Thank you for listening to this webinar entitled What Works Clearinghouse Webinar on Evidence-Based Practices and Programs in STEM.
Today, you'll hear from experts and educators about what Works Clearinghouse resources that support educators to select and use evidence-based practices in their classrooms and schools. We will first provide an overview of the What Works Clearinghouse and its resources for educators. Next, we will illustrate how these resources can help you identify and use evidence-based practices for STEM instruction. Finally, we will show you where to find these and other What Works Clearinghouse resources for educators and decision makers. The What Works Clearinghouse, or WWC, was established to be a central and trusted source of scientific evidence for what works in education. The What Works Clearinghouse reviews existing research in education, determines the quality of the research, and then summarizes findings from the high-quality research. The goal is to help educators and decision makers identify and implement evidence-based programs and practices. All What Works Clearinghouse resources are free to use. What Works Clearinghouse resources include practice guides, which provide educators with actionable recommendations on how to apply evidence-based instructional practices and address challenges in their classrooms and schools. Practice guides include examples that are ready to use in your classroom. Intervention reports support schools, districts, and educators in selecting evidence-based interventions. Use these reports when deciding, for example, whether to adopt a specific supplemental math program. Intervention reports summarize all high-quality, publicly available research on a specific intervention and discuss the costs and implementation of the intervention. Individual study reviews provide the ingredients to practice guides and intervention reports and show how the What Works Clearinghouse rates the quality of each study. Although individual study reviews can also support evidence-based decision-making, findings from one study may not represent all that is known about the effectiveness of an intervention practice. More comprehensive summaries of evidence are found in practice guides and intervention reports. For an infographic with more information about these What Works Clearinghouse products, please see the description for this webinar on the YouTube page or see the links at the end of this webinar. Now we will share examples of recommendations and action steps from practice guides that can help educators implement evidence-based instruction in their classrooms. Lynn Fuchs will begin with an example from the recently released practice guide on assisting students struggling with mathematics.
My name is Lynn Fuchs. I'm a professor of special education at Vanderbilt University, and I study instructional methods for improving mathematics and reading outcomes for students with learning disabilities. Today, my focus is the What Works Clearinghouse practice guide that addresses students who struggle with mathematics in the elementary grades. And today I'll give you a glimpse into this practice guide by briefly discussing two of the guide's recommendations. On this screen, you see one recommendation from the guide. Educators should use the number line to facilitate learning of mathematics concepts and procedures, to build understanding of grade level material, and to prepare for advanced mathematics. The number line is a unique mathematical representation because it can concurrently represent all real numbers, including whole numbers, fractions and decimals, and positive and negative numbers. And it's a powerful tool for helping students develop a deep understanding of the number system and for supporting their learning of advanced mathematics. As explained in the practice guide, before using a number line with elementary students in the early grades, we recommend that teachers introduce students to a concrete version of a number line, like a number path students can walk on, or like game boards or clotheslines. These concrete examples help students begin to form a visual image of what a number line looks like. After introducing the physical number line with a series of individual units lined up on a path, connect that idea to a number line on paper or projected on a screen, while the students identify similarities and differences between the representations. And teachers should be sure to direct students' attention to the distance from 0 to 1 and explain how that distance represents the length of one unit. This will help students understand that the 1 on a number line is not just a tick mark. Instead, it refers to the 1 unit distance from 0. Another recommendation from the practice guide is to provide deliberate instruction on how to solve word problems, which deepens students' mathematical understanding and support their capacity to apply mathematical ideas. One important idea for carrying out this recommendation is to teach students to think about word problems as belonging to word problem types. A word problem type includes all problems with the same mathematical structure. For example, consider the problem on this slide. Brian sold 9 cups of lemonade on Monday and Tuesday in all. How many cups did he sell on Monday? This word problem belongs to the combine or total problem type because the mathematical structure involves combining parts to form a total. The teacher introduces each new problem type one at a time using a story that includes all quantities without a missing number for students to find. The full story helps students think deeply about what the word problem type and the quantities mean. Next, the teacher presents a word problem. It's the same story, but with a missing number. As the teacher and students discuss the story and the word problem, the teacher uses role-playing, gestures, and concrete objects to help students visualize how the quantities relate to each other and what the mathematical structure of this problem type means. Then the teacher shows students other word problems in the same problem type using different scenarios and numbers, so students see how the problem type stays the same even when the scenario and quantities change. After helping students understand the problem type, the teacher teaches a solution method for solving that word problem type. Solution methods can include graphic organizers, diagrams, or equations that represent the problem type's key underlying mathematical structure. On this slide, you see a combined problem and a solution method where an equation represents the combined problem type. Part 1 plus part 2 equals the total, or P1 plus P2 equals T. Students read the problem to categorize it as a combined problem, and they write the combined equation. While reading the problem again, they also circle the numbers they need to solve the problem, and they cross out any numbers they don't need. They identify which number is P1, which is P2, which is T, and what the missing quantity is. They use a blank line to show where the missing number goes. Here, students use a graph to find some of this information. Once they fill in the numbers and write a blank for the missing quantity, they have the calculation problem that solves the word problem. Note that identifying a problem type is different from determining what operation solves that problem. For example, a combined problem requires addition when the total quantity is missing. But in the problem on this slide, the combined problem requires subtraction because one of the parts is missing. Also note that as teachers introduce each new problem type, They systematically expand understanding of the problem type, and they actively teach the vocabulary and language constructions often used in that word problem type.
Next up, John Starr will talk about examples from another math-focused practice guide.
I'm John Starr, a 7th grade math teacher and a professor of education at Harvard University. I study children's learning of mathematics in middle and high school, particularly in algebra. One practice recommended in the Algebra Practice Guide is to use solved problems to engage students in analyzing algebraic reasoning. Solving algebra problems often requires students to think abstractly, particularly requiring students to process multiple pieces of complex information simultaneously. This can impose a high cognitive load on students, which can interfere with their ability to learn. Solved problems, also known as worked examples, can minimize the burden of abstract reasoning by allowing students to see the problem in many solution steps at once, without executing each step, thereby helping students to learn more efficiently. When I use this instructional approach with my students, I often write or project the solved problem on the board, and then ask a student to come up to the board to describe the steps that they've taken in the solved problem and to explain the reasoning that has been used. Then I would use the students' responses to encourage a class discussion. I might ask students questions such as, why do the steps work in this order? Would they work in a different order? Could the problem have been solved with fewer steps? Can anyone think of a different way to solve this problem? Will this strategy always work, and why? When students are comfortable with the reasoning behind the steps in the solved problem, I might extend their learning by presenting an incorrectly solved problem for students. I would display the incorrectly solved problem by itself, or display it side by side with the correct version of the same problem, clearly labeling the problem that's solved incorrectly. I would engage my students in a discussion of the error and what steps led to the incorrect answer. Another What Works Clearinghouse resource based on the Algebra Practice Guide provides tips to parents and caregivers for supporting algebra learning at home, but you can use these tips in your classroom as well. In addition, the document provides algebra examples that can help parents and caregivers understand some of the math that your students might see at school. Algebra can seem like it's all about symbols and unreal abstract math. Many students make better sense of what they're learning in algebra when there's a context associated with the material. Even for what might seem to be the most symbolic and abstract idea that's taught in algebra, such as the distributive property, we can find context that give it meaning. Parents can look for ways to incorporate these contexts to help your students make sense of the abstraction. For example, a problem on the home tips document shows 2 strategies to figure out how much to expand a garden in your yard. In this example, you currently have room to plant 1 flower per square foot, or as shown in the diagram, 6 flowers total. But you'd like to extend the garden to make it big enough to plant 15 flowers. To solve this problem, you need to calculate the current total area of the garden, as well as to figure out how much we need to expand. Currently, you can see that the garden is 2 feet long and 3 feet wide. You might have students draw a picture of the problem to help visualize it, as we've done here. You want to figure out how many feet longer than 2 feet you need to extend the garden to make it large enough to plant 15 flowers. Thus, we can write an equation that says 3 times 2 plus x equals 15. Once we write this equation, there are several different strategies we can use to solve it. One approach that you can use is to use the distributive property. In this case, which you see on the left of the screen under strategy 1, you would multiply 3 times 2 added to 3 times x, which is equal to 15. Using the distributive property, this can be rewritten as 6 plus 3x equals 15. Solving this equation, if we subtract 6 from each side, we have 3x equals 9. Then if we divide each side by 3, we're left with x equals 3. In other words, this means that we need to extend the length of the plot by 3 feet to a total of 5 feet in order to plant 15 flowers. As a second way to solve this same equation, which is labeled strategy 2, instead of using the distributive property, you can solve this equation by dividing both sides of the equation by 3. Starting with this same equation, 3 times 2 plus x equals 15. We divide each side by 3. This leaves us with 2 plus x equals 5. Now, subtracting 2 from each side, we arrive at x equals 3. The answer is the same using either strategy.
Next up, Jane Porath will talk about examples from a What Works Clearinghouse practice guide on teaching fractions.
Hi, I'm Jane Porath and have been a middle grades mathematics teacher for the last 25 years. I'd like to describe an example of one of the recommended instructional practices from the Fractions Practice Guide. Students are most proficient at applying computational procedures when they understand why those procedures make sense. Although conceptual understanding is foundational for the correct use of procedures, students often are taught computational procedures with fractions without an adequate explanation of how or why the procedures work. I take the time to provide such explanations and to emphasize how these procedures transform the fractions in meaningful ways. In other words, we should focus on both conceptual understanding and procedural fluency and should emphasize the connections between them. The practice guide recommends several practices for developing understanding of computational procedures, including use of visual representations and estimation to reinforce conceptual understanding, providing students with opportunities to estimate or judge the reasonableness of their answer, and addressing common misconceptions and setting problems in real-world contexts. I'll provide an example of using estimation. Estimating with fractions is one way to focus on both conceptual understanding and procedural fluency, and to emphasize the connections between them. Estimation requires students to use reasoning skills and thus leads them to focus on the meaning of procedures for computing with fractions. One way to estimate is through benchmarks, numbers that serve as reference points for estimating the value of a fraction. The numbers 0, 1/2, and 1 are useful benchmarks because students generally feel comfortable with them, and I encourage my students to think about whether a fraction is closest to 0, 1/2, or 1. Sometimes I ask students to share their initial estimate and to explain their thinking before they compute the answer. For example, when adding 7/8 and 3/7, students may reason that 7/8 is close to 1 and 3/7 is close to 1/2, so the answer will be close to 1 1/2. Alternatively, if dividing 10 by 5/6, I would encourage my students to reason that 5/6 is close to 1 and 10 divided by 1 is 10, so the solution must be a little more than 10. This strategy is likely to be most useful with problems in which a solution cannot be computed quickly or easily. There is no point asking students to estimate the answer to a problem that can be solved quickly and accurately by mental computation, such as 7/9 subtract 5/9. Teaching students effective estimation strategies can maximize the value of estimation for deepening understanding of computations involving fractions. The Fractions Practice Guide provides many more practices and strategies to help teachers further develop their fractions instruction.
Now we'd like to transition to examples of What Works Clearinghouse intervention reports that can help districts, schools, and teachers identify evidence-based programs to improve students' STEM skills. The What Works Clearinghouse has dozens of intervention reports that provide information on the effectiveness of specific products or programs. For example, a recent intervention report provides information on a program called Fraction Face-Off. Fraction Face-Off is a supplemental math program developed to support fourth grade students who need assistance solving fraction problems. Teachers use program materials with individual students or small groups to promote understanding of the magnitude of fractions, to compare two fractions, to put three fractions in order, and to place fractions on a number line. This intervention had strong research evidence, and the What Works Clearinghouse found it has potentially promising effects on student achievement. One issue I'd like to pause and mention here is the What Works Clearinghouse's careful attention to conflicts of interest. One of our panelists, Lynn Fuchs, is a key developer of the Fraction Face-Off intervention. Lynn had no involvement in the What Works Clearinghouse's review or rating of the intervention. In fact, when there is a study or intervention up for review, the What Works Clearinghouse makes sure the reviewers are not affiliated with the study, nor can reviewers be involved in using, promoting, or developing the intervention itself. Similarly, intervention report writers are checked to make sure they had no involvement in developing the intervention or conducting the study. This further helps ensure the What Works Clearinghouse's ratings and conclusions are not influenced by any conflicts of interest. Next up, Erin Furtak will discuss a What Works Clearinghouse intervention report about a science program.
My name is Erin Marie Furtak, and I am a professor of STEM education and also Associate Dean of Faculty at the University of Colorado, Boulder. And I also got into this profession as a high school science teacher. I taught high school earth science and biology. And I'm really glad to talk a little bit about some of the included science interventions that positively affect student achievement. The first is an intervention report that was recently released on a science intervention called STELLA. STELLA is a professional development program developed by BSCS Science Learning that aims to improve students' science achievement by improving teachers' science content knowledge and their abilities to explain science concepts to students, clearly identify to students the science concepts used in student learning activities, and engage students in thinking about science. STELLA is offered to teachers who provide science instruction to students in kindergarten to grade 12, and training is also available for school or district personnel who wish to become STELLA professional development leaders. STELLA is a year-long professional development program for teachers that begins with a 2-week summer institute that's 60 hours long, followed by 8 monthly grade level study group meetings during the school year, which are 30 hours long. And personnel who wish to become STELLA professional development leaders require an additional 1 to 2 years of training. Teachers who participate in STELLA learn from post-secondary science faculty to improve their knowledge of the science content areas they'll teach during the school year, to become familiar with STELLA lesson plans and instructional strategies, work in study groups led by STELLA professional development leaders to analyze video recorded examples of experienced teachers implementing STELLA lesson plans and strategies, and video record their own classroom instruction and meet with their study group to analyze one another's video recorded lessons. And I can say, speaking from experience, watching myself teach science is really an incredible learning experience, as well as working with other teachers to watch each other's video recorded lessons. So it's great to see how that's a part of the STELLA experience. The intervention report is based on one study that met WWC standards, which shows that STELLA has a potentially positive effect on student achievement. And I've had a chance to work with BSCS in learning about STELLA firsthand as part of an NSF project I'm involved with other teacher education programs in my area. STELLA encourages teachers to analyze classroom practice, and this includes examining the science content storylines in the units they're teaching, including identifying learning goals, thinking about content representations, and linking the activities they're doing with those learning goals. It also builds on a deep research base that acknowledges the importance of asking questions that draw out students' ideas and experiences as key starting places for science teaching. along with asking probing questions that really challenge students to grow in their thinking, in addition to engaging students in reasoning about observations, as well as using students' ideas and kind of applying them in a wide variety of situations and contexts. So you can see how a lot of these elements of Stella are actually really consistent with a lot of efforts that we're making as we move toward the next generation science standards. The second product I wanted to talk about is an individual study review on playground physics, which is a technology-based app and classroom curriculum designed by the New York Hall of Science to support middle school students' science engagement and learning of force, energy, and motion. The program includes professional development, the app, and a classroom science curriculum. The app allows students to record and review videos through 3 lenses that include motion, force, and energy. The curriculum integrates informal and formal inquiry-based learning strategies to promote greater student knowledge and understanding of physics. The program was designed to be implemented in a formal school setting during the regular school day. The study examines the impact of the playground physics program on student learning of physics concepts, student engagement, and science-related attitudes. The study met WWC standards and found statistically significant positive effects on student physics knowledge.
The What Works Clearinghouse also occasionally summarizes interventions that are popular in use but do not meet current What Works Clearinghouse research standards. For example, the What Works Clearinghouse recently produced 2 intervention reports for 2 science interventions, even though no studies met the What Works Clearinghouse's research standards. The first report is about project-based inquiry science, or PBIS, which is a science curriculum for students in 6th through 8th grades. PBIS has approximately 13 instructional units, each covering a topic in life science, earth science, or physical science. Students using the curriculum work together in small groups to conduct hands-on explorations, read relevant informational texts, reflect on what they have learned, and apply new knowledge. The second report is about Full Option Science System, or FOSS, which is a science curriculum for students in kindergarten through 8th grade. The curriculum includes content in physical science, earth science, and life science, and consists of multi-week modules in each grade level. In both cases, the What Works Clearinghouse is not saying that these curricula are ineffective. Instead, the issue is that we do not have enough information that meets What Works Clearinghouse standards to know whether the curricula are effective. Therefore, the What Works Clearinghouse produced a report on both curricula that says it's unable to draw any research-based conclusions. When additional high-quality research is published on these 2 curricula, the What Works Clearinghouse will review the new research and update the intervention reports based on any new conclusions that can be made. In addition to intervention reports, the What Works Clearinghouse also publishes individual study reviews. Like the playground physics example that Erin discussed, this slide shows an example of an individual study that compares 2 mathematics practices for students in 7th grade. Individual study reviews like this one are the ingredients that go into practice guides and intervention reports. But users can also access the results of these individual studies to learn about the quality of research and the findings about effectiveness in a single study. This could be useful if there is an intervention of interest that has been reviewed but does not have a full intervention report. However, the findings for a single study may not tell us everything about the intervention's effectiveness because there may be other studies that the What Works Clearinghouse has not reviewed that may come to different conclusions. Given a choice, users should always defer to an intervention report or practice guide. Individual study reviews might also be useful if the user wants to know about findings for a specific type of setting or population included in a specific study. Lastly, I'd like to provide key What Works Clearinghouse resources for STEM educators, administrators, and policymakers. To support using What Works Clearinghouse practice guides and intervention reports, the What Works Clearinghouse has a wide variety of resources, including infographics, videos, and webinars with information about how the What Works Clearinghouse develops practice guides and how educators can use them. You can also find videos and written materials that provide educators with additional support for implementing recommendations from each What Works Clearinghouse practice guide. Resources draw from the What Works Clearinghouse evidence to highlight actionable recommendations educators can use to address classroom and school challenges. The materials developed from practice guides go in detail on the specific practice guide guidance about how to integrate practices and programs backed with strong evidence in your schools and classrooms. We provided several examples of that guidance today. Other resources are available on the What Works Clearinghouse website, such as a webinar on assisting students struggling with math, a video on developing effective fractions instruction for elementary and middle schoolers, and a guide with tips for improving mathematical problem solving in 4th through 8th grades. That concludes the content of this webinar. This slide and the next 2 slides provide helpful links to the What Works Clearinghouse website, including the home page, the landing page for the full library of practice guides, the landing page for the full library of math intervention reports, and the landing page for the full library of science intervention reports. Thank you for attending this webinar and for your interest in the What Works Clearinghouse STEM resources. If you have any questions about the What Works Clearinghouse, the practice guides, interventions, or any other What Works Clearinghouse product, please reach out to the What Works Clearinghouse Help Desk through the What Works Clearinghouse website, which is linked on this slide. This webinar and related resources will be available online at the What Works Clearinghouse website for future reference.